Imagine you're on a super-fast train, hurtling down the tracks at an incredible speed, and you throw a ball forward. To you, it moves at 10 miles per hour, but to someone on the platform, watching you whiz by, it's the speed of the train plus the ball, a simple addition. That's Newton's world, a world of predictable motion. Speeds add up like ingredients in a recipe. Everything is relative to the observer. Your perspective shapes what you see. But then came light, a game changer. Light doesn't play by these rules, it's a rebel. In the late 1800s, scientists, with their meticulous instruments, measured the speed of light and found something shocking, a cosmic anomaly. No matter how fast you move, whether you're standing still or breaking the sound barrier, the speed of light is always the same, unwavering and absolute. Whether you're racing toward it like a moth to a flame or away, desperately trying to escape its reach, light's speed never changes. It's a universal constant. This defied all common sense, every intuition we have about how the world works, and cracked the foundation of physics, shaking its very core. If you chase after a ball, it appears slower, its relative speed decreases. But with light, it doesn't matter. Your motion is irrelevant. Its speed is absolute, a fixed point in the universe. This constant speed, this cosmic speed limit, about 300,000 kilometers per second, a mind-boggling velocity, is called c, a simple letter representing a profound concept, the universe's speed limit, a barrier we can never truly break. Nothing with mass, no matter how powerful our technology becomes, can ever cross it. The mystery of c set the stage for a revolution in physics, a paradigm shift. It hinted that our understanding of space and time was incomplete, that there were deeper truths to uncover. The constancy of light was the key, the Rosetta Stone, that would unlock a new vision of space-time, a universe far stranger than we could have imagined. A young patent clerk named Einstein, working in relative obscurity, would soon change everything, rewriting the laws of physics. The universe was about to get a lot stranger, more mysterious, and infinitely more fascinating. Before Einstein, scientists believed light needed a medium to travel through, like sound needs air. They called it the luminiferous ether. The ether was thought to fill all space, providing an absolute frame of reference. If it existed, Earth's motion through it should change the measured speed of light. Enter Michelson and Morley in 1887. They built a precise experiment to detect the ether wind. They split a beam of light, sent it in two directions, and looked for a difference. They found nothing. The speed of light was the same in all directions, at all times. This failed experiment was a disaster for the ether theory. Scientists tried to patch the theory, but nothing worked. The ether became a ghost, haunting physics with no solution. The universe refused to reveal an absolute frame. The Michelson-Morley result demanded a new way of thinking. The stage was set for someone bold enough to throw out the ether entirely. That someone was Einstein. Physics was about to be reborn. Enter Albert Einstein, a patent clerk with a radical idea. He asked, "What if the speed of light is always constant, no matter how you move?" He proposed two postulates. The laws of physics are the same for everyone in uniform motion, and the speed of light in a vacuum is the same for all observers. Instead of explaining away the Michelson-Morley result, he embraced it. If light speed is always CE, then time and space themselves must be flexible. Our clocks and rulers aren't fixed. They depend on how fast we're moving. This was the birth of special relativity. It applied to observers moving at constant speeds, not accelerating. Suddenly, time could slow down, space could contract, and mass and energy were two sides of the same coin. Einstein threw out the ether and Newton's absolutes. The universe was now held together by a single, unwavering constant, the speed of light. Reality itself had changed. If the speed of light is constant, a fundamental law of the universe must bend space and time to keep it that way, warping the very fabric of existence to uphold this cosmic speed limit. Imagine a spaceship flying at 90% the speed of light, a truly mind-boggling velocity. From Earth, observing this incredibly fast journey, your clock appears to tick slower relative to the ship's clock. This difference in the passage of time is what we call time dilation. Furthermore, your ship also appears shorter in the direction of motion, seemingly compressed from our perspective. This visual compression is known as length contraction. Inside the ship, however, everything feels perfectly normal. The astronauts experience time and space as they always have. But to an outside observer, watching from a stationary point, you're in slow motion inside a squashed ship, a bizarre consequence of approaching the speed of light. Why does this happen? Picture a light clock, a photon bouncing between two mirrors. On the ship, from the astronaut's perspective, the photon simply goes straight up and down, a short and direct path. From Earth, however, it travels a longer diagonal path because the ship is moving horizontally as the light bounces vertically. Since light speed is constant for all observers, the only way to reconcile this difference in path length is for time to slow down for the moving ship relative to Earth. Space and time are not independent entities, but are woven together into a single fabric, space-time. The faster you move through space, the more you're prioritizing spatial movement, the slower you move through time, as your journey through the temporal dimension is reduced. We're all constantly traveling through space-time at the speed of light, with most of our journey directed through the dimension of time. When you move fast through space, you trade some of that constant space-time journey away from time and towards space. This is the heart of relativity. Motion through space fundamentally affects your passage through time, linking the two inseparably. Space and time are not separate and distinct. They're a single, four-dimensional fabric, a unified entity. The universe is a cosmic dance, a delicate balancing act between space, time, and the speed of light, the ultimate cosmic constant. Our reality, at its deepest level, is far more flexible and interconnected than we ever imagined. The rules may seem strange and counterintuitive, but they're beautifully consistent and universally applied. Welcome to the mind-bending world of space-time. To see time dilation in action, imagine twins, Stella and Tara. On their 20th birthday, Stella rockets to a star 5 light-years away at 99.5% the speed of light, then returns. For Tara on Earth, the trip takes just over 10 years. But for Stella, time slows dramatically. She experiences only 1 year. When they reunite, Tara is 30, but Stella is just 21. The twins are no longer the same age. This isn't science fiction, it's a real prediction of special relativity. Stella has time traveled into Earth's future by moving very fast through space. But isn't motion relative? Shouldn't Tara be younger from Stella's view? The answer is in the journey. Stella accelerated, turned around, and changed frames. Tara stayed put. The symmetry is broken by acceleration. The traveler always ages less. The universe keeps a separate clock for each of us, ticking at a rate set by our path through space-time. Time travel, in a sense, is built into the fabric of reality. Special relativity sets a cosmic speed limit, an absolute barrier in the universe. Nothing with mass, no matter how advanced our technology becomes, can reach or exceed the speed of light. It's a fundamental constraint. Why? What makes this speed so special and insurmountable? Einstein's famous equation, E=mc², the cornerstone of modern physics, reveals that mass and energy are interchangeable, two sides of the same coin. As you accelerate an object, imparting kinetic energy, it gets heavier. Its mass increases. The closer you get to light speed, the faster it goes. The more energy you need to accelerate it further. Near light speed, its mass approaches infinity, requiring an infinite amount of energy to reach c. To reach CE would require infinite energy, an impossibility, impossible in our universe, governed by the laws of physics as we understand them. Only massless particles, like photons, the fundamental particles of light, can travel at light speed. This speed limit has deep consequences. It shapes our understanding of the cosmos. No warp drives, at least not as we imagine them in science fiction, no instant galactic travel. Interstellar journeys remain a daunting prospect. The speed of light enforces causality, the fundamental principle that effects can't happen before causes. The order of events is preserved. If you could go faster than light, you could, theoretically, arrive before you left, a concept that leads to breaking the order of time, creating paradoxes that defy logic. The universe protects its logic, its very structure, with this ultimate speed limit. Information, energy, and influence can never outrun light. It's the ultimate cosmic governor. The cosmic speed limit is not just a number, it's a fundamental aspect of reality. It's the guardian of reality, ensuring the universe remains consistent and predictable. The laws of physics are safe, protected by this unbreakable barrier, and so is the flow of time, preventing the universe from descending into chaos. Light's speed is the universe's unbreakable rule, a constant that underpins everything we know. If nothing can move faster than light, why do some galaxies recede from us faster than CE? The answer: special relativity limits objects moving through space, not the expansion of space itself. The universe is expanding. Space stretches like a rubber band. Galaxies aren't moving through space faster than light. The space between us is growing. The farther a galaxy, the faster it recedes because more space is stretching in between. Some galaxies are so distant, their light will never reach us. The expansion outpaces even light. This doesn't break Einstein's rule because the galaxies themselves aren't moving locally faster than light. It's the fabric of space-time that's stretching. If you were in a distant galaxy, you'd see others receding too. The expansion of space is a global phenomenon described by general relativity. The universe's rules are subtle, but they hold. We talk about light's speed, but what about darkness? Is it a thing? Does it move? In physics, darkness isn't a substance, it's just the absence of light. Light is made of photons, real particles that travel at c. Darkness is what's left when photons aren't there. It has no energy, no speed, no substance. When you turn off a light, the last photons travel across the room at light speed. Then, nothing. The arrival of darkness is just the moment the last photon passes by. Darkness doesn't move, it's simply the absence of moving light. You can't send a beam of darkness or a darkness signal. All information and energy must be carried by something physical, like photons. The speed of light is the ultimate limit for all influence in the universe. Darkness is the canvas. Light paints the universe we see. The cosmic drama unfolds at 300,000 kilometers per second. Before Einstein, we believed in absolute space and time, a clockwork universe. Special relativity shattered that view, revealing a flexible, interconnected space-time. Our experience of reality depends on our motion through it. This revolution isn't just theory, it powers our technology. GPS satellites moving fast above Earth experience time differently. Without relativity, your phone's map would be useless. EMC2 explains how stars shine and how nuclear energy works. Particle accelerators must account for relativity as they push particles near light speed. Einstein's real legacy is his approach, question assumptions, trust experiments, embrace the universe's strangeness. Special relativity was just the beginning. General relativity would follow, describing gravity as curved space-time. Together, these theories form the foundation of modern cosmology. They are a testament to human imagination and the power of a single, stubborn fact: the speed of light. The universe is stranger and more beautiful than we ever dreamed. And it all began with a cosmic speed limit.